Hello! Last week I did a video of a simple pendulum swinging using rigid dynamics to get the force and apply that joint force to a bearing load in static structural to see the stress in the link or pendulum. This week I've been asked to talk about a tilted pendulum, so the force going through the pin is more complicated. I've done that two ways, once with a revolute joint and once with a shoulder bolt with full contact. So let's look at the shoulder bolt with full contact first. So here's a contact that's frictional between the pin and the hole, and there's also contact between the shoulder and the back of the link. So the pin we're going to hide for now. We're going to also talk about the fact that this has, though the geometry is aligned to the global coordinate system, gravity is acting at an angle, and the opposite of gravity is acceleration, so gravity is going down in the minus z direction by using an acceleration force that's going up at 1g. The link itself is going to have to pivot in the plane of this tilted plane because there's a tight fit between the pin and the hole, and that tight fit actually is driven by not by the geometry. I could have made the pin a little smaller than the hole. That's one way to do it. What I did instead was edit the offset in the pin contact to have 0.1 millimeters of radial clearance around the hole. So that's dialed in by typing in numbers, which makes it easy to adjust the clearance if you want to see the effect of that on the result. You'll also see that there's a friction on both the shoulder and the pin, and that's going to eat up energy that would be taking away from the swing. So we'll look at the swing first, and that is the right here. We see that the thing swings down and has lost all of its energy, and friction brings it to a halt. What's the interesting part here is the stress distribution. So I'm going to hide that body so we can look at the stress. And what we can see at the end is that this is again in a tilted plane. So the clearance has allowed the contact to develop on the bottom of the hole on the back of the link and the top of the hole at the front of the link, and on the back of the link the shoulder is touching this area as well. And so we have a very realistic distribution of stress by using full contact, and that stress plays out while the link is operating. So we can see that here. What I want to do is contrast this stress distribution, which is very realistic, with what happens on a revolute joint, which does not try to have realism, but it does make the simulation run faster, and that is this. So it's the exact same model, but there's no friction per se. There is instead on the joint a torsional damping, so it's a more smooth operation. And so when the link swings with damping, it smoothly reduces the amplitude of the swing. So that's one characteristic you can do with a revolute joint, but the stress is nothing realistic. If we look at how the revolute joint works, there's one node at the center, and that node has a spider going to every node in the hole, and that hole has those spiders are defined as rigid. So the whole circle there, the inner face is a rigid body, and therefore the stress is not rendered very realistically. So what we see here is a very small stress, basically on the wrong side of the, and not taking into account any of the difference caused by the tilted plane. So that's why we wouldn't use a revolute joint to get accurate stress results. So I guess looking at the back side here, this is the end of the demonstration. I hope that explains some differences between revolute joints and full contact, and how stress can be evaluated in a dynamic simulation, including all the inertia effects. Thanks for watching.